Hello and welcome everyone. My name is Rick Frage. I'm the sales director at SFTec. Thank you everybody for joining today. This webinar titled Competitive Properties of SFT Glass Fiber Reinforced Polymer, GFRP Spacers, will be presented by Dr. Ahmed Elbady. So Dr. Ahmed, he studied civil engineering and graduated with a bachelor's degree from the faculty of Mataria in Egypt University. That was back in 2010, where he graduated with a gold medal. He was the first on his group. So gold medal basically for his academic performance. Later on, he pursued his master's of technology in construction engineering from Helwan University, also in Cairo, Egypt. Then he came to Canada to pursue his PhD in civil engineering at the University of Sherbrooke in Quebec. Here, he basically he specialized or researched the behavior of structural concrete reinforced with fiberglass polymers or with fiber reinforced polymers, testing and characterizations of FRP materials, tunneling reinforced with FRP bars and FRC, and nonlinear finite element analysis of reinforced concrete structures. Dr. Ahmed is a senior structural researcher at SFTec. We are based in Montreal, for those who don't know, in Montreal, Quebec, Canada, and a MITAX postdoctoral fellow at the University of Sherbrooke. During his time with us, he assisted us in many projects. He's still assisting us in some ongoing projects too, regarding concrete, of course, projects reinforced with SFT-Bar. Some of the projects he worked on during his career, that was before SFTec. He worked on tower buildings, multi-story residential, commercial, and industrial buildings, water tanks, Grand Egyptian Museum, ministries, buildings, and a Cathedral of the Nativity of Christ. This is the largest cathedral in the Middle East. Whereas at SFTec, he helped in different projects, from structural slabs, ICF wall design, precast elements. He converted different plans from steel design to FRP, and he also took on some designs from scratch where he designed the whole building or structure in FRP. The experience and knowledge have definitely been felt at SFTec and contributed to our progress.
Thank you very much, Rick, for the brief introduction. And I would like to express my gratitude to all the audience for their participation. Hello, everyone. Today, it's my pleasure to present a short webinar on SFTec glass fiber reinforced polymer GFRP spacers and show their competitive properties compared to those existing in the market. Here is the outline of my presentation, beginning with introduction. Then I will provide a concise overview of FRP spacers and emphasizing their advantages and applications. This will be followed by an examination of the SFT-Bar spacers under compression testing. Additionally, I'll present a case study on the available spacers in the market to compare the properties with our product, and finally highlights conclusions and some recommendations. Who are we at SFTec? We are associated with Shandong Safety Industries Co. Limited, who are specialized and focused on manufacturing fiber reinforced polymer products. Our products are mostly designed in Canada and are manufactured in China. We work with national and international engineering firms. We work with them through the design process and help them with the fiber reinforced polymer design standards, whether they are in Canada or in the US. We are developing strategic partnerships in Canada, in North America in general, and all over the world. Our main focus is parking facilities, garages, water treatment plants, and retaining walls. However, we have involved with different projects, including bridges, tower communications, bases, basically almost everything. Our primary goal is to focus on the applications of glass fiber bars in the carbon straps, aiming to raise awareness of FRP solutions as alternatives to steel on the market. FRP bars are non-corrosive material and alternative to corrosive steel bars. SFTec FRP bars are made from composite materials, fiberglass or carbon fiber, and is manufactured by filtration process using a mix of recycled fibers and resins with superior quality and different aspects. These figures show a microscopic view of the FRP bar. There are three different types of FRP bars, or actually we have four different types: carbon, armide, glass, and basalt. The basalt is not in the curve. However, the stress strain curves shows how these three main types of FRP bars are compared with steel. 2 points should be noted from these curves. First, the glass FRP bars have lower strength compared to the other two FRP bars. Second, the strength of all bars is higher than that of steel bars. However, their behavior is linearly elastic until failure. Glass is the most popular one because it's already 2 or 3 times stronger than steel. However, in terms of budget, it is definitely cheaper than the other three FRP types. Regarding our products, we can produce different types of FRP products depending on the project requirements. Actually, we mainly focus on GFRP bars in different shapes, including straight bars, spiral stirrups, circle and square ties for transverse reinforcement, bent bars, and everything necessary for diverse multidisciplinary projects. Also, as you can see on the right side of the screen, we can produce glass FRP shell connectors for sandwich panels. Also, we introduce carbon sheets for restoration purposes and alkali glass fiber for reinforced concrete, providing significant improvements in resistance to harsh soil conditions. As we mentioned before, the glass FRP bars are widely used due to its production cost and its better tensile strain compared to other FRP bars. So, just to sum up the advantages of the SFTec glass FRP bars over the conventional steel bars, FRP bars have longer surface life because it's corrosion resistance. Therefore, it improves durability in harsh environments, such as constructions near coastal area in North America cold climate. The FRP bars have better resistance against corrosion compared to steel bars. As told earlier, the tensile strength of FRP bars are 2 or 3 times more than that of steel bars. However, it have more tensile strength. FRP bars are 4 times lighter due to low density compared to steel bar, and this is a big advantage in different projects. Due to corrosion resistance, FRP bars are good for harsh chemical environments, as well as it's neutral to electrical and magnetic disturbances, useful for many applications such as airport, military applications, MRI rooms, and hospitals. Now, let's move on to the next slide. There are some of the selected field applications of the SFTec FRP bar we have already done in Canada. GFRP reinforced concrete waffle flooring slabs designed with SFTec glass FRP bars, which was built in Halifax, Nova Scotia. It can be used also for slab on grades. It's non-structural slab, it's 1x1 replacement, and it saved a lot of money compared to steel bars in terms of labor and transportation. Another project shows the cast on-site precast sandwich panels, and they have used our glass FRP bars in their project as reinforcement in China. And in the right side is retaining wall built for the city of Montreal. The retaining wall was designed to dump snow with the icing salts during the winter. And so they built this retaining wall with the SFTec glass FRP bars, which provided resistance against the chemical used in the icing salts, and they're getting a lot of attention in this field application. Now we will delve into the role of FRP spacers in building structures. What is FRP spacers? The FRP spacer is a profiled rod made of fiber reinforced polymer material to eliminate thermal bridging in double walls and to ensure uniform thickness dimensions of insulated double walls. When producing an insulated double wall, the GFRP spacer is inserted through pre-drilled holes after placing insulation on the fresh concrete. The length of the GFRP spacer used therefore defines the thickness of the wall to be manufactured. The GFRP spacers also needs to fit within the insulation, maintaining a vertical position. This ensures it can bear the full load of the wall post-insertion while ensuring dimensional stability. As you can see in the pictures, it can be used in double masonry wall, RC insulated walls, or a combination of both. What are the areas of application of the GFRP spacer? GFRP spacer is used for thermal insulation purposes in the core insulated double wall industry for masonry or RC panels. GFRP spacers also can be used in situ and precast tilt-up wall panels or concrete sandwich panels used for slabs or walls in residential and commercial single or multi-story buildings. GFRP spacers are used to connect the three layers, which can bear the load of wind, earthquake, etc. Now let's explore the advantages of GFRP spacers as alternative solution to steel ones. High resistance against corrosion, such as alkali effects, chemical attack, and moisture. The lightweight of GFRP spacers compared to steel, cost-effective as low assembly costs due to quick and easy installation. It is considered a non-conductive and magnetic-free material. Due to the profiling, the bar achieves high pull-out and punch-through resistance. This part of the webinar is devoted to examining the SFTec bar connector or spacer under compression testing. Why is it important to determine the compression load? Number one, the required characteristic value for use in precast plants is the sustainable load. As number two, as mentioned earlier, the GFRP spacer should bear the full load of the wall before the insertion process, as well as the load of wind and earthquake. According to STM D695, the test method is usually used when evaluating the compressive properties of rigid plastics. However, the standard is not applicable to round GFRP bars. Moreover, there is no existing standard test method to characterize the properties of GFRP bars under compression. For sampling and specimen production details, this testing program aims to determine the compressive load of the number 4 13mm G60 GFRP spacer manufactured by SFTec Canada. 3 samples for each unpressed length of 300, 400, 440, and 500 millimeter. Both ends of the GFRP bars were inserted into 95 millimeter steel tubes with cement grout filling the gap between them to provide the confinement. These photos show specimen fabrication details. For all compression tests already done at the structural lab in the University of Sherbrooke, the ultimate compressive strength was measured or calculated from measured data using the MTS machine, as shown in this figure. Based on the literature, the axial load was applied at a rate of 1.5 millimeter per minute, as adopted by Aljamra et al. 2019 for GFRP bars under compression. The tests were video recorded to accurately preserve the overall behavior of the bars during the entire loading. Now, let's explore the results of our test in terms of compressive strength and failure modes. The results of all compression tests are summarized in this table. Moreover, the figure on the right side shows the maximum recorded compressive load during the test. The ultimate compressive strength decreased with increasing the unpressed length from 210 to 86 megapascal. The observed failure modes will be presented in the following slides. The first failure mode was a crushing failure observed in the tests of the shorter specimens with unpressed length of 300 millimeter. In this type of failure, the bars separated and buckled individually. The second failure mode appeared to be a combination of buckling and crushing modes for specimens with unpressed lenses of 400 and 440 millimeter. The buckling type failure would occur first, and under continued loading would be followed by a crushing failure in the same specimen. The third failure mode was pure buckling of the entire bar for specimens with unpressed length of 500 millimeter. In this type, the resin matrix and the fibers of the GFRP bars buckle as a single entity. Next, let's move on the 2018 case study conducted by PT Innovation on spacers made of glass fiber reinforced plastics. In this study, 10 samples were tested with the same unpressed lens using our testing methodology. The bar was clamped in two sleeves and loaded with a high displacement rate. In terms of failure modes, the dominance of glass fiber failure at support points diminishes and deflections begins noticeably later in GFRP at 300 and 360 millimeter lenses. However, GFRP spacers longer than 360 millimeter show early signs of deflection, with buckling of the bars becoming a less significant failure criterion. Based on the comparison between the performance of our SFTec bars and the case study, SFTec spacers demonstrated a 24% increase in the ultimate compressive load for lenses of 300 and 400 millimeter. Moreover, the 440 millimeter spacer exhibited an 86% higher ultimate compressive load. According to Euler formula, the theoretical buckling load can be obtained from this equation. All SFTec connectors have a buckling load higher than the theoretical maximum load at buckling. Now, the conclusions. Use of GFRP spacers or connectors in construction has many advantages over the conventional steel spacers. GFRP spacers panels can help minimizing the effects of thermal bridging. SFTec spacers exhibited higher compressive strengths compared to existing GFRP spacers. Buckling strengths of SFTec spacers higher than the theoretical buckling and decreased with increasing the unpressed length. This product is available at SFTec Canada as a SFTec bar connector or spacer, and our company recommends it for all double insulated walls with several dimensions and several diameters. Thank you for your attention.
Thank you very much, Dr. Ahmed. Thank you, everybody, for participating. We did receive a few questions, but as we said, we're going to address them at a later time. Thank you, everyone, and have a wonderful day.